Yeah, so I uploaded the slides for chapter 3. So this part is the linear regression. So a part of it is review, but I add some more explanation compared to the stat 50/30. Yeah, so the data science is really more practical, the way to think about data analysis. So we have the more practical issues in chapter 3. Okay, so still we cover some review of the linear regression. Yeah, so you can see the slides in Canvas, so you can download it. Yeah, so the most of the essential features of the linear model have already been discussed in stat 50/30. If you don't really remember, you can download the 50/30 slides in Canvas. And also the chapter 2 of the course, just the last week, we covered the sum of the linear regression. So I focus on some specific things. So one is the LM function. LM functions outputs which have not been discussed in 50/30 or in chapter 2. And also the how to check assumptions of the linear model and how to deal with violation on assumptions. For example, if we have some pattern in residual plot, how to handle it, that we discuss it in more details. And also maybe this is covered in some of other courses such as 50/30 or 68/40, but how to handle the qualitative, the categorical predictors. So basically we have to prepare the dummy variables, that is the indicator variables. So if we have variables such as the blood type, we have the 4 blood types, the A, B, O, and AB. So we have 4 blood types. So in such a case, basically we have to prepare the 3 indicator variables for A, indicator variables for B, and indicator variables for AB maybe. Then we can handle the qualitative, categorical predictors into the quantitative scheme. So yeah, so the point is that we have, okay, so y and x. So in linear regression, the y is the categorical, the y is the response, the continuous response. And we have the predictor x1 to xn. And y should be continuous. That is the linear model assumption. So this is continuous numeric variable. Sometimes maybe discrete, but still so the increment is small enough so that the y can be regarded as continuous. For example, the age, people's age is sometimes reported as an integer, but still it ranges from maybe 0 to 100. So it's, we have the small increment, so we can deal it as a continuous variable. So, but the x1 to xn, so usually this is continuous, but even some are the categorical variables, still that we can handle these variables. So the important point is just y should be continuous. X doesn't really matter. Okay. Yeah. So, okay, so just at first, some review of linear regression. So this is a typical linear regression output. So we have the data set. So data set is in this CSV file. Usually CSV file is separated by comma within each rows. And the header is equal to true. And okay, so we read the data. So data, the DAD, so data for advertisement has I think at least the 3 columns. So that it looks like the sales and the TV and radio and some amount such as 100 or 50 or 30 and so on. And there may be second line 200, 80 and 40 and so on. So this is the DAD data set. Then we regress the cells on the TV and the TV square and radio. So remember that if we want to include the square of some column, so TV square, so that means the 50 square or 80 square, you have to put I to make it as a variable. Yeah. So usually the outside of LM function, just the TV square works. But in linear model, the square sometimes means the interaction terms. So if we have x1 and x2 and x1 plus x2 square, that means the term such as x1 square, x1, x2, and x2 square. So to distinguish these two elements, I mean, just the value of x1, the value of the square of x1 plus x2, we want to distinguish that from these variables, so that we have to put I. So we regress the cells on 3 variables, the TV and the square of TV and radio. Then this is the output. So maybe the first quiz, how many observations in the data set do you think? Actually, yeah. Anyone can see? If you're shy, then you can use the chat function and you can answer the question.
198.
Sorry?
198.
198?
Yeah.
Close, but it's not. Anyone else?
Is it 197?
197? Okay,
Yeah.
so it's close, but slightly different.
I would say 200.
Yeah, 200. Why?
Oh, because of 4. Yeah.
Well,
yeah.
I see there's 190, like residual standard error. I see there's 196 degrees of freedom. And then you have 2 variables and then 1 that's squared. So I figure that's about 4.
Yeah. So 196 plus basically the number of parameters here. So we have the 4 parameters here. So we lose 4 degrees of freedom. So 196 plus 4, that is original number of observations. Yep.
And when computing that, the intercept counts as one of the variables?
Yes.
Thank you.
Yeah, so intercept, yeah, that's a good question. So intercept is a kind of variable you can see. So sometimes we explicitly have the intercept as a variable, but the intercept is basically 111. So mathematically speaking, basically, this is also another variable. Yep.
If we were to say the data was centered and the intercept was 0, would you still count it as a variable?
Data is centered. No. If it's centered and then we drop the intercept from the design matrix, right? So that we drop from the list of predictors, so we don't include it.
Oh, okay, thank you.
Yep. Yeah, so yeah, often the machine learning people, they centered the data, ignore the intercept, so even they standardize the data so that all variables have variance 1. But yeah, so here still we have the non-centered data. So we have 4 variables. So you can see the 4 lines in this output. So we have the 4 degrees of freedom lost in this case. So 200 observations. Okay. So and you can see that these are the estimate. In the next page, I will explain a little more. But these are the coefficient, and these are standard errors. So yeah, maybe you can just see. So cells, maybe a little small. Okay, so this output means the cells is equal to the 1.288. So that is here in the previous page, plus 0.07844 times TV. So that is here. And minus the 0.0001137 times the square of TV. That is here. This is negative 1.1136 times 10 to the power negative 4. So that is 0.0001136. Then the radio, 1.93, okay, here. And the standard size of error is indicated in the next column here in the previous page. So the standard error size is 0.3588. So typically we have the error size of 0.35. So yeah. And the here the -3, so 0.00498. And here the standard deviation is the even one digit smaller, 0.0000167. And here standard deviation is very small, the 0.007293. Yeah. So if we think about the standard deviation, actually these numbers are significantly different from 0. So for example, 1.288 with standard deviation 0.3588. So even we have the 2 standard deviation of this estimate, still the intercept is positive, probably at least 0.5 or 6. And maybe at the most, maybe 2 or something. So the, you can see how reliable these estimates are. Yeah. So in a common sense, if we see this, okay, so maybe this 8.8 doesn't mean anything, but at least we can say intercept is, yeah, probably around maybe 1 point something. Yeah. And we often use this notation, y is equal to f of x plus epsilon. So f is this part, so the part of y explained by predictors, and epsilon is an error. And here we say p is equal to 3. In some books, the intercept is also included in the predictor. So we say p is equal to 4. But in this chapter, at least, we say p is equal to 3. And we have 3 predictors, TV and the square of TV and radio. Sample size 200. Okay, so now that we want to see some other outputs. Do you have any questions so far? Okay. Yeah, so some other outputs. Maybe the first one. What's this? The residuals? Yeah, that is residuals. So residuals are basically the epsilon hat in the next page's notation. So y is equal to f of x plus epsilon, but after we estimated f, we can estimate epsilon also. That estimate is epsilon hat, and this is the distribution of epsilon hat. I mean, some characteristics of the distribution of epsilon hat. If we have very small number of observations, then R lists all residuals. I think at least if the number of observation is 5 or less, then they list all observations, all epsilon hat. And if sample size is larger, then we can see only minimum, median, maximum, and first quartile and third quartile. So you can see that median is, this is the error, median of the errors, and I mean the residuals, so almost always 0, but slightly negative. So indicating probably it's skewed to the left a little bit. Median is smaller than mean. And actually the minimum is very small, so maybe some outliers on a negative side. The positive side, 3.57. That is moderately large, not too extreme. Usually 95% of residuals are within ±2. And first quartile, third quartile, not much information here. Yeah, so that is the residual. So yeah. Yeah, so original equation is here, but the f is actually unknown. So we estimated f hat. We estimated the coefficient of each predictor. So if we replace f by f hat, then we can get epsilon hat. That is estimate for epsilon, not exactly equal to epsilon. Yeah. So if this has this kind of the extreme value, then you have to be careful because this affects the regression results a lot. So maybe some outliers here. Yeah, so this is the histogram of the residuals. The residual series is represented by this. So this is the series of 200 residuals, epsilon 1 hat to epsilon 200. Then this is residual plot. So it's almost the good, almost symmetric distribution, ranges from maybe -3 to 3. So slightly heavy-tailed distribution than normal. But yeah, I think that these observations are extreme. So the two observations. If residuals are normal, then almost we never see the -4 or -8. So some outliers. Yeah. Yes. Yeah, and that's possible. So even if you make advertisement, maybe the because of some reason, just the sales does not go up. Maybe the company bankrupt after making advertisement, or I don't know, but that's possible. Okay. And the next one is residual standard error. So this output is just after the estimated coefficients. So residual standard error is 1.517 on 196 degrees of freedom. So what does it mean? That is y is equal to f of x plus epsilon, then size of epsilon. So that means the expected size of epsilon square, or variance of epsilon. So this is estimated as 1.517 square. So I would say variance, estimated variance. Yeah, that is 1.17. So if we take square, then we take square, so the 1.517 square. So if we take square root, then that is the standard deviation. So if epsilon is normal 0 sigma square, then the sigma hat is 1.517. So that is a kind of error size. If model is correct, that is estimated irreducible error size. That is 1.157. Yeah, of course, the sales of some product cannot be totally explained by advertisement, by TV, radio, and the newspaper. So that's natural that we have some positive error. Yeah, and how to estimate this sigma hat? That is estimated by this formula. So basically, this is similar to variance formula because this is estimated variance. But the different thing is we have estimated parameter here. Okay, sorry, I think this isn't really entirely correct. So this should be estimated. It's beta not hat to beta p hat. So we have the p plus 1 estimates used. So these are estimated. So that means that it makes this squared residuals artificially small. So think about we have 2 observations and we have 2 parameters. Okay, then even if error is positive, still the residuals are 0 because we can adjust beta naught hat and beta 1 hat to make residuals 0. So we need some adjustment here. So n minus number of observations, n minus this p plus 1. Then we can estimate the size of sigma without any bias. I mean, estimate of squared sigma without any bias. And this residual divided by sigma hat, this follows the t distribution with degrees of freedom 196. So t distribution is defined by the distribution of this. So this is the definition of t distribution. If z and z1 to zk are all independent standard normal distribution, then this distribution follows. So this random variable follows the t distribution with dfk, degrees of freedom k. So the point is that here the epsilon hat and the sigma hat are both random. So epsilon hat is almost normal 0,1, so it's similar to this z. But the sigma hat is estimated variance, and that is basically similar to this shape. So both numerator and the denominator have variability. So this does not follow normal anymore. So epsilon follows normal. Epsilon follows normal 0 sigma square. So epsilon divided by sigma follows normal 0,1. But the sigma is estimated. So in such a case, this becomes t distribution. So when the denominator is random, so usually it becomes heavy-tailed distribution, because denominator is random means if denominator is just very small number by chance, then the ratio epsilon hat over sigma hat, it becomes very large or very small number. So that makes distribution the very the heavy-tailed. And the t distribution has heavier distribution than normal. So normal distribution is round-shaped, or mound-shaped, maybe we say. And the t distribution is more like this. Okay, so if you flip this, then this becomes almost t. It's not the reason that it's called t distribution, but it looks like t. Yeah, t distribution is called t because the original paper on t distribution was published by the anonymous author named Student T. So that's why. Yeah, so sorry, so the residual standard error is 1.517. So here is the estimate. Yeah, so epsilon and epsilon hat have the different distributions. So epsilon follows normal distribution, but the epsilon hat follows t distribution, so it was different. So we can imagine the situation. So I talked a bit, but we can imagine the situation that we only have two observations. So still that we have epsilon 1 and epsilon 2, and those follow a normal distribution. But if you fit the regression, we have x here and we have y here, and we have two observations here and here randomly, then okay, so fitted line is here. So this is the y is equal to beta naught hat plus beta 1 hat x. So that means epsilon 1 hat is equal to 0 because this line goes through these 2 points. And epsilon 2 hat maybe, okay, so this is x1 maybe. This is x2. Then also we can say epsilon 2 hat is equal to 0. So that means if we have two parameters, two observations, then actually the distribution of epsilon hat is equal to 0. So this distribution, this is the probability of epsilon hat is equal to 0 is equal to 1. So this distribution. So it's different from original distribution. So original distribution is normal 0 sigma square. So it's totally different. Yeah. So actually, if the n is equal to 2, p is equal to 2, then epsilon hat follows epsilon hat divided by sigma hat follows t distribution with df0, but the df0, we cannot define t distribution. So anyway, we cannot think about it, but if n is slightly larger, there's still that we can see what's the distribution of epsilon hat is. Yeah. Do you have any questions so far? Okay. So this is the t distribution. Yeah, t distribution. So the normal distribution is in a black line. So this black line, black curve is normal density function. And the t distribution, the three examples are here. The yellow one is the most, have the heaviest tail. The t distribution is df1. And the purple one, the df2, and the blue one, df5. If degrees of freedom is maybe more than 30, almost it's indistinguishable with normal distribution. So normal distribution is t distribution with degrees of freedom infinity. Yeah, you can see originally the distribution, the definition of t distribution is here, z1 square plus zk square over k. And if k goes to infinity by law of large numbers, this quantity just converges to expectation of z1 or zi square. So yeah, so that just becomes z, and it becomes normal. So do you know the variance of the t distribution with df1? It looks at least have heavier tail than normal. Anyone knows the variance of t1? No? Anyone? Just guess.
Is it 1?
1? Anyone else? So, okay, so at first, okay, t distribution is similar to normal. So, okay, 1 is maybe the baseline, right? But you can see the t infinity. So this has variance 1. So yellow one has heavier tail, so it looks variance is larger.
Possibly 2?
2? Okay, any other? Any other people? Andrew, do you know answer? No? Maybe no. Is Andrew here? No. Okay, or any other people who maybe have taken 6840 or yeah, so if we see the shape, okay, so, plug in k is equal to 1. That is the z1 over z2, basically, maybe z over z1 or something. So independent normal distribution on both denominator and numerator. Yeah. So t distribution, you can Google it, and the proof is not that simple, and the variance is infinity here. So sample variance is always, the finite number, but the actually the variance, the expected, the value of the squared, the error is infinity for t distribution with df1. Even df2, still variance is infinity. How about df5? This is online environment, so you can cheat by using internet. How about df5? Do you know the variance? Actually, the df3 and larger, we have the variance. And actually, the variance is equal to 5 divided by 5 minus 2. So that is 5 over 3. So n over n minus 2 is the formula for variance. So this goes to 1 as degrees of freedom goes to infinity. Yeah, so T distribution has very heavy-tailed distribution, but the 1 and the 2 is especially heavy, have a heavy-tailed. It does not even have the variance. Okay. The sample variance, of course, exists, but the expected, the value of the squared epsilon does not exist. Okay, so next, the adjusted R square and R square. So the linear regression reports the multiple R squared and the adjusted R squared. So these are a similar number. The always adjusted R square is smaller. R square is called coefficient of determination. So this is actually defined as this 1 minus SS error over SS total. SS error is this, basically error size. So this is equal to summation of epsilon I square. So the error size, maybe epsilon I hat, sorry, the epsilon I hat square. And SS total is total variation. So yi minus y bar. Y bar is just the average size of response. Yi is just each response. So the all variation in response. So variation in response. And this is the residuals. So the part which is not explained by the model. So this is basically the proportion that the variation of y is not explained by predictors. So 1 minus this is the variation which is explained by the variables. So the proportion in variation in y explained by predictors. Okay. So that is multiple R squared. One friend in my former workplace asked me why this is proportion in variation in y explained by predictors, and just we defined our English sentence as this. So the original definition is this, and the verbal explanation of this 1 minus SS error over SS total, sometimes that we explain in this way in English. So if you cannot understand the English sentence, just that is because of the definition of this sentence. Okay, so just this is the truth. And sometimes we are not good at using the equation to understand the concept, so that we use just a sentence to explain this. Okay. So if you understand this part, that's totally fine. So this is just another way to more inaccurately explain the situation. Okay. Okay, so multiple R square is here, and the adjusted R square are slightly different. We have just adjustment term. So how many of you have heard of adjusted R square before?
I have.
Oh, you have?
I've used it for model comparisons to, yeah, because it corrects for the R squared, just increasing every time you add a predictor. Yeah.
Yep, great. So do you have any experience that adjusted R square is negative? So at first, the multiple R square is the proportion in variation explained by predictors. So that is between 0 and 1 always. So this is in 0 and 1, right? Maybe close interval 0 and 1. How about adjusted R square? Can it be negative? can it exceed 1? Anyone? Have you ever seen the negative adjusted R-square? You want to explain why by x1, x2, x3, and you ended up to get the adjusted R-square of negative 0.02? Yes, no?
I remember once when my R-squared was 0, and then
Okay.
the adjusted became negative.
Okay, yes, okay, yeah, you're right. So multiple R-square is 0, then by the definition, so the numerator will be inflated, right? So because the smaller the divisor. So actually the adjusted R-square becomes negative. And actually in the real research, once I see the adjusted R-square of negative 0.02, so really X is useless to explain why. So adjusted R-square, a good thing is it adjusts the number of predictors. So we have more predictors, then it's natural that R-square gets larger, right? So just sometimes, just by chance, by coincidence, the X explains Y for the existing training data set. So we can adjust that term by dividing by the smaller number here. But yeah, the one problem is that that can be negative. So it does not exceed 1, because the adjusted is smaller, but this can be negative. Yeah, you can do some simulation, generate random numbers, then you can get the negative R-square, adjusted R-square sometimes. Yeah, so the concept of adjusted R-square is to penalize a large number of predictors for fair comparison of models with different number of predictors. Still, the adjusted R-square favors a larger model as a tendency, but still, I mean, at least the adjusted R-square consider that the size of the predictor, the number of predictors. And in what sense R-square is adjusted? And here is the answer. The expectation of adjusted R-square is 0 if all predictors have no relationship with Y. Okay, so all predictors are useless. We want to get R-square is equal to 0, right? And the adjusted R-square, actually, the expectation is 0. So if x1, x2, x3 have no information on Y and just random numbers, then we regress Y on x1, x2, x3. Adjusted R-square is sometimes 0.01, sometimes negative 0.01, on average 0. So in that sense, adjusted R-square is adjusted. Yeah, and R-square is by definition between 0 and 1. Adjusted, not necessarily more than 0. Okay. And okay, so the next question, so why R-square is called R-square? And actually, that is because we use R for correlation coefficient, and the correlation square of correlation coefficient is equal to multiple R square. So yeah, multiple R square is also called the coefficient of determination, and that is just square of correlation coefficient if we have one predictor. So suppose we have only X and Y, and that we regress Y on X, then multiple R square is 0.332. Then if we think about correlation between Y and X, and we square it, then we have the same number here. So that's why we say this as R squared. But of course, the multiple R squared is more a general concept because we can have more than one predictor, and adjusted R squared, they even modified more. Yeah, so next one, F test. So we think about this kind of line. Maybe the first regression result also have the similar thing. And the F statistic of 719. Actually, this doesn't have to be integer, and probably this is just rounded. Truth is maybe 718.23 or something like that. 718.73 or something like that. And the so this represents the overall fit of the model. In total, that model, linear model, is useful to predict Y or not. And the p-value is very small, so that means it's useful. So basically, okay, so Y is equal to beta naught plus beta 1 x1 plus beta p x p plus epsilon. And this is the null hypothesis. And the alternative hypothesis is that at least one of beta 1 to beta p is not equal to 0. Yeah. So intercept is ignored, so it's not included in the test, but it's included in the model, but it's not included in this hypothesis. Okay. So yeah, so we test this. So in total, this model is useful in this case. And this test statistic F is given by this formula. So SS total minus SS error over SS error. We have some adjustment term, but okay, so for now we ignore it. And the denominator, it's a kind of error size, the sum of squared error size. And this is the total variation minus error size. So basically the variation explained by predictors. Explained by predictors. So variation explained over error is F. So that ratio is F. So if F is large, a larger proportion of variation is explained by predictor. So that means large F predictors are more useful. Okay, so yeah, so that means that for large F, we reject null hypothesis to support the regression model. So null hypothesis is the no coefficient is different from 0, so that is model is useless. So if large F model is useful, so we should have more significant result, smaller p-value. Yeah, so this is the F, and this is some adjustment term to adjust the degrees of freedom. So SS error have the degrees of freedom of n minus number of observations. So that is here. And P is the number of predictors. So so more predictors, of course, we can explain the more variation. So we divide the total variation by the number of predictors to standardize the result. Yeah, so we should reject null hypothesis if F is large. And how large? And actually, this F statistic follows the F distribution. Sorry, we have some. Yeah, so it doesn't mention, but this F statistic follows F distribution with degrees of freedom P and n minus P minus 1. Okay. So F distribution is defined by random variable, I would say x1 square, x2 square up to xp square divided by p, and the y1 square, yq square divided by q. And here, x1 to yq are independent, normal 0, 1. So this is the F distribution. So maybe to be exact, the F distribution with df, degrees of freedom, p and q. So this is defined by this distribution. So since we know the distribution of this F is F sub p n minus p, we can decide the threshold. Okay, so this is the distribution of F. Okay, distribution of F. So if F is large enough, to be exact, if F falls in this range, we reject null hypothesis. Otherwise, we don't reject null hypothesis. And here is the, okay, so this threshold is determined that this area determined so that this area is equal to some specific small number, such as the 0.05. So if the significance level is 0.05, then this area should be 0.05, and we reject null hypothesis if the F value is larger than this. So this is the the scheme of statistical test. And another way to test is to get the p-value. So if we have observed F value, so in the last example, that was 719, then we can calculate this area. So that is p-value. And the last time that was very small number. So this is smaller than 2 times 10 to the power negative 16. And if this p-value is less than 0.05, then we reject null hypothesis if the significance level is set at 0.05. So the scheme is the same in the previous page and this page. Just the way of the reporting the result is different. So usually the R reports p-value. So if p-value is less than some threshold, we reject. Sometimes we pre-specify the significance level here, then we see whether or not we reject H naught. But using p-value is more convenient because we can set the significance level after we see the result. I mean, maybe you should have the specified number, but the different people have different significance level. So at least the reporting p-value is more convenient for more people. Also, if we see p-value, if p-value is 0.0001, that is much stronger result than the p-value of 0.01. So in the past few years, many people complained the use of p-value, p-hacking or something like that. Have you ever heard of it? P-hacking, yes, the p-value hacking.
Yes, I've heard of it.
Oh, okay, yeah. So,
yes.
Yeah.
When you adjust the p-value that you deem acceptable to, say, pass your whatever research you're doing.
Yeah. So So the p-value is traditionally set at 0.05, and what people do is they prepare the data set 1. Okay, so then calculate p-value. Okay, p-value is 0.06. Okay, so unfortunately we cannot do that. Okay, so then they collect another data set, data 2. The p-value is 0.07. Okay, so still it's not significant. And data set 3, p-value 0.04. Oh, okay, so then we publish the result. So that happened many times in science, probably in the biological science. Okay, so that isn't really honest way, right? So you have to specify the design first, and you have to set the threshold first. I mean, significance level first. But sometimes people just try many times until you get the significant p-value. So that is called the p-hacking. So yeah, so we should we should set the significance level first, and we should set the design and the sample size first. Then after that, we do analyze the data. Of course, a larger sample size means, more higher probability to reject null hypothesis. So that is true, but still we need some reasonable scheme to fairly judge whether or not the null hypothesis is rejected. Yep. So F distribution have two parameters. So we have different shape depending on the number of degrees of freedom. And there are several types here. Okay, so again, the F distribution is defined by the distribution of ratio of the two random variables. So distribution of this is F distribution with DFPQ. And both are the average of the independent random numbers. So you can see that this part, okay, so this part, so this converges to expectation of yi square as q goes to infinity. And yeah, the denominator also goes to some constant, but for now, we think about this as just the average of random numbers. So this approaches to normal by central limit theorem. So that means, okay, so if denominator is large, then numerator is, numerator, sorry, the numerator, yes, the numerator, yes. So numerator, the somewhat large degrees of freedom. So P is somewhat large. And the Q is large, then FPQ approaches to normal. Okay. So you can see if D1 and D2 are both 100. So this is the distribution of F sub D1, D2. D1 and D2 are both large. So this is close to normal. Close to normal. So if both are really large, it concentrates on 1. So almost it spiked at 1. So it converges to 1. But yeah, degrees of freedom is large, it's almost normal. But the small, it's different. If the D2 is 1, actually this is very skewed distribution. So monotone decreasing PDF. Moderate range, then we have the skewed distribution, skewed to the right. Yeah, so F distribution is also a ratio of two random variables. So, and both are positive. So, and that means the very heavy-tailed distribution and skewed to the right. And it's never negative. Both numerator and denominators are positive. So it's never negative. So that is F distribution. Do you have any questions on F distribution?
Sorry, I have a question.
Oh, yeah, sure.
Well, the P was the number of variables. What was the Q?
Here, P and Q are just integers. So just I want to define the distribution of P sub P, F sub PQ. So P and Q are just the general integers. So natural number.
And not related to number of variables or number of data?
So here, in this slide, I just explained the general definition of F distribution with P, the degrees of freedom PQ. So it's nothing related to the number of observations. And yeah, in the previous page, we have some specific numbers. So here, P is number of predictors. and n is number of observations.
Okay, thanks.
Sure. Any other questions? Yeah, so the F distribution, the idea of the distribution is that both are variance, right? So the sum of the squared random variable is basically similar to variance formula, right? So the variance. So this F random variable represents the ratio of two variances. The ratio of two variances are important, right? For example, think about the precision of two different models. Then we compare sigma 1 and sigma 2. Or we compare the two linear models, and the sigma 1 and the sigma 2 are the variance of error size. Then we compare the error size of two different models. So the comparing variance is very common topic, and the F distribution is often used. But F distribution, the density function is very complicated, and we have the formula for the mode and variance and so on. So you can check the Wikipedia. I don't even remember it. Yeah. Yes. So in the previous example, okay, so we see this line, F statistic is this. So this means the F statistic follows degrees of freedom 719 and 3. And yeah, and the F statistic is pretty large. So F distribution is basically centered around 1. So especially if we see this case, it's centered at 1. Other cases, it's very skewed, but this is a kind of center. So for example, the blue line, it's skewed to the right, and the median is much smaller than 1. But you can expect the expectation is much larger because it's skewed to the right. So it's centered at 1, okay, because the denominator, both numerator and the denominator, okay, and both expectation are 1. Okay, so expectation of numerator is 1, expectation of denominator is 1. So in some sense, it's centered at 1. It's not exactly expectation, because expectation of x over y is not equal to ex ey. So we cannot say expectation of F distribution is 1, but at least we can say denominator and the numerator, both expectation are 1. So it's a kind of centered at 1. So that means 719 is very large. Yeah, and actually the p-value is very small, so null hypothesis is rejected. Okay, so that is the 3.2a. So the basics of linear regression. Do you have questions? So I explained that basically almost all outputs in the LM function. Yeah, here. So the residual, this is the distribution of residual, and this is the output. Maybe, yeah, so we can explain this. So basically estimate and the standard error. This t value is the ratio. Okay, so estimate divided by this is equal to this. 1.288 divided by 0.358. So this is 3.58. It looks just by chance, so this number and this number are similar, but yeah, just that is a coincidence. And this is p-value. So how significant this t-value is. So, or we can say how significant this estimate is different from 0. And all values are significant. So the relationship between cells and the TB, square of TB, radio are pretty robust. and very meaningful. And residual standard error, degrees of freedom, multiple R squared, adjusted R squared, and F statistic, and degrees of freedom, and the p-value. Yep. So now you can see all meaning of these data. Additional statistics are possible that to use. You can deduct some additional outputs using some additional function on LMB. For example, the AIC of LMB returns Akaike information criterion of this, or some other functions. Okay, so now this 3B. Yeah, so now that we discussed how to check assumptions of the model. So, okay, so suppose this is the model, original model. Then basically assumption is here. So error term is normal and independent and identically distributed. Okay. So independent means they're not related to each other. For example, that we pick up the one child from each grade in the elementary school, and that we gave them mathematics test. Then we measure the scores. Okay, so maybe the 5th graders get better score than the 1st grader, but at least those 5 students are not related, so independent. Okay. So that is independent, and identically distributed means that we have the same distribution. Same distribution. So suppose that think about the temperature at noon in Singapore. Okay, Singapore is almost on the equator, so the temperature is the same throughout the year on average. Okay, so distribution is identical, so identically distributed. Maybe the today's temperature and the tomorrow's temperatures are highly related, but if we don't think about that relationship and just think about the distribution of one day without any additional information, then each day we have the same distribution, so that is identically distributed. So the 5 children's math test score example, not identically distributed because the different grade have different expected score, but independent because 5 students are not related. The temperature, daily temperature at noon in Singapore, it's not independent because tomorrow's temperature and today's temperatures are somewhat close, but those are identically distributed, but because without any information, the distribution of the temperature is the same. Okay, so there are several possible violations. So one is the nonlinear relationship between predictor and response. So think about the maybe the height and weight of some animal. Probably the relationship is like this, so it's not linear. And second, the correlation of error terms, especially the some observations are not independent, then errors are correlated. You think about the temperature or your body temperature throughout the day. Maybe just after the meal, your temperature is higher, and okay, you fit the straight line. Then these 2 observations, errors are correlated. Both are positive, both are negative. Non-constant variance, heteroskedasticity. Yeah, for example, in the stock market, if some big news happened, for example, the last year in February or March, then stock market is very volatile. So the daily return is sometimes very, very large positive or negative values. In some period, it's very mild like this. So size of variation is different depending on the season. So non-constant variance. Outliers, normal assumption means that not many outliers, but sometimes we have outliers, very large or very small epsilon. Or also the outlier for x. Okay, so some x values are really large, maybe just because of error. recording error. High leverage points, typically we have several observations here, but the one observation here, then almost this observation determines the regression line, probably like this. Okay, so leverage, high leverage points, and also the collinearity. Two variables are very close, so that we cannot distinguish these two. For example, so maybe so sometimes the two variables are very similar. So for example, we explain the weight of some animal by height of some animal and maybe width of the animal. Then, okay, so this and this are very similar variable, almost proportional. So it's really hard to distinguish how much H contribute to explain W or how much the width explains the W. So we have to think about these problems when we estimate the parameters. Do you have any questions about these concepts such as non-linearity, correlation, non-constant variance, outliers, and so on? I have questions. So how many of you have heard of the high leverage points?
I think I'm sort of familiar with them.
Yep, thank you.
Yeah.
And I think I explained it in, okay, yeah. I think I explained it in the stat 6840, but the other courses, probably not much. Maybe 50, 30, maybe not. Collinearity, how about collinearity? How many of you have heard of collinearity before?
I have heard of that.
Yeah.
Okay, great.
Likewise.
Yeah. I think that should be explained
Yeah.
in any courses, any the data-oriented courses if you studied linear regression. Yeah, collinearity is important. Sometimes we say multi-collinearity. Yep. Okay. So at first, the non-linearity. How to check non-linearity? So when residual plots have some pattern in trend, then it implies that more information can be extracted from X to explain Y. So, okay, so example here. So this is the residual plot. So this is fitted value, Y hat, and residual epsilon hat. Okay. So fitted value, okay, so think about the case of one example of one predictor, then that is beta naught hat plus beta 1 hat X. So almost you can think about it as X. Okay, so just the predictor against residuals. Okay, predictor against residuals, and it has some pattern. Okay, so these are estimated error. So on average, this is 0. On average, this is 0. But you can see, so this line, this trend line is just the average of the, the local observations. I'm not exactly sure how they calculated it, but probably, for example, this value is the average of maybe 15 closest observation to here. So that's the average is here. So then we do that for all observations, then the curve is here. And you can see some curvature here, not straight line. So that means probably the X square, if we include X square in the predictors and we fit Y is equal to beta naught plus beta 1 X plus beta 1 X, beta 2X square, then we can explain the Y better. So this is actually the mile per gallon on the horsepower example. So this relationship, rather than this relationship, that we should have this regression model. So if we include this the quadratic term, actually this is pretty consistently close to 0. So residual plot should not have any pattern. So if we have curvature like this, then we should investigate the maybe a more variable or maybe transformation. Sometimes y is beta naught plus beta 1 log of x or square root of x, and so on. Yeah, so the first thing you have to think about is transformation. So often the case is that we have x here and y here, and the plot is like this. So even without fitting regression model, you see obvious needs to the transform variable. In this case, the tendency is like this. So probably maybe I would say y on square root of x, maybe, or something like that. Yeah. Maybe more typical case is the other way around. So like this, maybe a little clearer. Then probably we should take logarithm of y on x, or maybe square root of y on x, or something like that. Okay. So y, the scale, y value is much larger when x gets larger. So probably log of y or square root of y is more appropriate way to transform. Or maybe if we have x and y and many observations are concentrated around here, but only few observations around here, even few observations here, then probably log of y on log of x. Sometimes we have 0 value or slightly negative value. So in such a case, it's a little bit hard to decide, but maybe log of 1 plus y on log of 1 plus x, or just be creative. Yep. Yeah, so next we discussed the correlation of error terms, but I think that it's already the 8:15, so we stop here and we continue to discuss the chapter 3 next time. Okay, so thank you for listening, and if you have questions, you can remain online and you can ask me questions.